In Chapter 12, we're looking at oxidation and reduction. We are going to be talking about how this pertains to organic chemistry. You've seen oxidation and reduction before, but we'll be looking at it from a organic chemistry perspective. I will bring it back to what it means in terms of bonding, but let's get started. So oxidation occurs when the number of carbon Z bonds increases, where Z is an element that is more electronegative than carbon. Or the number of carbon-hydrogen bonds decreases, and so that would be an oxidation. A reduction will occur when the number of carbon Z, again, an element that's more electronegative than carbon, when the number of carbon Z bonds decreases or the number of carbon-hydrogen bonds increases. So if we look at the most common reactions are where we're breaking bonds with hydrogen and making new bonds with oxygen, or where we're breaking bonds between carbon and oxygen and making new bonds with hydrogen. The more bonds with oxygen we have, the more oxidized. So carbon dioxide with 4 bonds to oxygen is going to be the most oxidized form of carbon. And the more hydrogen attached, so if we look here at methane, methane has 4 bonds going to hydrogen. That is the most reduced form of carbon. Now, if we look at this in terms of multiple bonds, which is going to be one of our primary things that we're talking about in this chapter, when we oxidize, when we are reducing an alkyne or an alkene, we add hydrogen to that alkyne or alkene to make it more reduced. So here is an example. If we have an alkyne and we add 2 hydrogens to it, we can get an alkene. That is a reduction. If we add another equivalent of hydrogen, we will get an alkane, and that is also a reduction. All right, so if we convert from an alkene to an alkane, that is also a reduction. If we go the other way, where we remove hydrogen, that is an oxidation. Now, that seems a little weird, but whatever the opposite of a reduction is would be an oxidation. If you're looking at a reaction and you're just not sure, well, the best way to determine it is to look at oxidation numbers. Now, your textbook doesn't talk about oxidation numbers, but I'm going to because I want you to understand it's a foolproof way of determining is something getting oxidized or reduced. So that foolproof way is to look at the oxidation numbers, and to get the oxidation number, it is going to be that the charge that an atom would have if you subtract the number of owned electrons from the number of valence electrons. Well, the number of owned electrons is going to be the number of electrons that are in bonds with atoms that carbon is what we're primarily interested in, that carbon is more electronegative than. For example, hydrogen. And if it's in a bond with something that is more electronegative than carbon, then that other thing will own the electrons. As an example, we are going to look at number, or before we look at number 32, we're going to look at this particular structure. And I have it drawn out, and so we can determine what the oxidation state of these 2 carbon atoms are. So carbon has 4 valence electrons. So we'll put 4 to indicate the number of valence electrons. And again, the reason it has 4 valence electrons is because carbon is in group 4 of the periodic table. So carbon has 4 valence electrons. And if we look at how many electrons this particular carbon owns, it's going to own electrons in bonds where it's more electronegative than the thing that it's bonded to. Well, carbon is more electronegative than hydrogen, so it owns both of those electrons. It also owns both of these electrons. The bond between the carbon and the oxygen, well, oxygen's way more electronegative than carbon, so the carbon doesn't own those electrons. When you have 2 carbons that are bonded to each other, they share the electrons equally, at least for at least for oxidation state purposes. So we're going to have half of those. So that's 1, 2, 3, 4, 5. So, and I'll put owned. So owned. And we'll do -5. So 4 minus 5 gives us an oxidation state of -1. If we look at this carbon, it's a little bit different. Again, it owns the electrons in the bond with hydrogen, but it doesn't own the electrons in the bond with chlorine. Chlorine's more electronegative, and then it owns half of these. So this one would be 4 minus 3, and that gives us +1. So that carbon that's on the right side is more oxidized than the carbon that's on the left side. Okay, so now that we've looked at that, I want to look at number 32, and we are going to come back to this page, so I'm going to keep that ready. Okay, so we want to look at number 32. Now, we're going to start by looking at does it gain hydrogen or lose hydrogen? Does it gain bonds with more electronegative atoms, or does it lose bonds? And in this case, these carbons here are going from not having much hydrogen on them to getting more hydrogen. So these are being reduced. All right, so these carbons are being reduced. So this is a reduction. So this is a reduction. Now, to determine what the oxidation states are, I went ahead and redrew these right here. So I redrew them. Again, carbon is in group 4, that's valence electrons. The number of owned electrons, well, it owns half of the electrons that it's in bonds with carbon with. So there's 4 bonds, so it owns 4 electrons. So this has an oxidation state of 0. The carbon on the end, however, is a little bit different. Still 4 valence electrons, because it's always in group 4. But it owns 1, 2, 3 electrons there, but it owns both of those electrons because carbon is more electronegative than hydrogen. So that'll be 5 minus 5. So that has an oxidation state of -1. Over here on the right side, we would say that it owns half of this and half of that, so that's 1, 2, and that it owns all of the electrons in the bonds with hydrogen, so that's 2 more and 2 more. So 2, 4, 5, 6, 4 minus 6 gives us -2. So the oxidation state of this carbon is -2. The carbon on the end has half of that bond, and then 1, 2, 3, 4, 5, 6 more. So 6 plus 1 is 7. 4 minus 7 gives us -3. So you'll see that both of the carbons got more negative. Their oxidation numbers got more negative. That means they've been reduced. If you just remember that when you gain more hydrogen, it gets reduced, that's going to get it done for you. But this is a foolproof way of figuring out the actual numbers. All right, if we look at this particular carbon has 1 bond going to oxygen and 2 bonds going to hydrogen. It loses both of those hydrogens and gains 2 bonds going to oxygen, so we'll get 3 total. So here, this is an oxidation. All right, so that carbon is being oxidized. Again, I've got it drawn out so that we can determine the actual oxidation state. All right, so 4 valence electrons. It owns both of those because it's more electronegative than hydrogen. It owns half of this one, and it doesn't own any of those. So 1, 2, 3, 4, 5. 4 minus 5 gives us -1. So -1 oxidation state on this carbon. We come over here to this carbon, and we'll find that it owns half of that bond, none of the electrons between carbon and oxygen, and none of the electrons between the carbon and oxygen there. So this one's going to be 4 minus 1 gives us +3. So we can tell because the carbon, its oxidation state got more positive, that carbon has been oxidized. So it's an oxidation. All right, here we're gaining a bond with oxygen on each of these, so we would predict that this is an oxidation. If you're getting new bonds to oxygen, it's going to be an oxidation. Again, we're going to look at the structure, the entire structure here. This carbon Scoot that up a little bit. So this carbon is identical to this carbon, so I'm just going to do one of them. So 1, 2, 3, it owns half of those, and all of those. So 1, 2, 3, 4, 5. 4 minus 5, -1. All right, and this one, like I said, is going to be exactly the same. It's identical. Over here, when we look at this, we've got, it owns both of those. It doesn't own that. It owns half and half. So 1, 2, 3, 4. So 4 minus 4 gives us 0. So we can tell because the carbon got more positive, its oxidation state got more positive, this carbon, these carbons are being oxidized. So that is an oxidation. Okay, now let's look at this. This is hydroquinone going to quinone. And so hydroquinone here, well, we're losing hydrogen, and we're making more bonds between carbon and oxygen. Making more bonds, we could predict that that is going to be an oxidation. Again, we're going to look at the oxidation numbers because that, as I mentioned, is a foolproof way of doing it. I have drawn out the carbons to make it more clear. All right, so carbon oxygen, it doesn't own any of those electrons. It owns half of these and half of those. So that's 4 minus 3 gives us +1. This carbon is identical, so it also has a +1 oxidation state. When we look at this carbon, it owns one of those bonds, or one of those electrons, one of those, but none of the ones in that. So this one's going to be 4 minus 2, +2. Since it got more positive, the oxidation state got more positive, these carbons have been oxidized. So these carbons have been oxidized. All right, so that's an oxidation. On this one, we've got, we're replacing the oxygen with a chlorine. And I'm going to go straight to this just to help on this. So if we look at this, the carbon, here's a carbon-carbon bond, so it owns half of that. It owns all of these electrons, so 1, 2, 3, 4, and it doesn't own any of these because oxygen is more electronegative than carbon. So 1, 2, 3, 4, 5. So 4 minus 5 gives us -1. If we come over here to this carbon, again, it owns all the electrons in the bonds with hydrogen, and it owns half of the ones in the bond with carbon. And since chlorine is more electronegative than carbon, then it doesn't own any of those. So this one is also 4 minus 5 gives us -1. So here, the oxidation state of carbon does not change. So this is going to be classified as neither. All right, so that carbon is neither oxidized nor reduced. All right, so let's go back. And we want to look at some reducing agents. We'll look at reducing agents in this first video, and in the next video, we'll look at some oxidizing agents. We'll find that when we're adding hydrogen, again, this is the most common thing that will happen when we're doing a reduction, is that we're going to add hydrogen to an organic compound. We'll find that there are 3 ways to do it. One way is to use just regular hydrogen with a transition metal catalyst. Often that transition metal catalyst is going to be palladium, but there are a couple of others that are possible. And I'll show you on the periodic table where those are, just real quick. All right, so here is palladium. Sometimes we'll find that platinum and nickel are also going to be good at doing this. There are some others that have activity with this, but we'll find that nickel, palladium, and platinum are going to be pretty good bets for catalyzing these reactions. All right, so we add hydrogen using a transition metal catalyst. We can also do what's called a dissolving metal reduction, and that uses alkali metal like sodium and liquid ammonia as our source of hydrogen. And so the electrons are literally added to our compound using the sodium. Sodium gives up those electrons and adds them. And then another reducing agent that we can use is something that's called hydride. And there are a number of hydrides. There's hydrides that are sodium borohydride, lithium aluminum hydride, and some related compounds that are similar to these two. The one we're going to talk about a little bit in this chapter is lithium aluminum hydride. In a later chapter, we will discuss sodium borohydride. And then also in a later chapter, we'll discuss some alternatives to sodium borohydride and lithium aluminum hydride that they change the reactivity. All right, so let's look at the reduction of alkenes. So carbon-carbon double bonds, and we want to reduce them by adding hydrogen to them. If you were to take an alkene, like let's say ethylene, and add hydrogen to it and not put in a catalyst, you would find that you would get no reaction. The transition state would be way too high and the activation energy would be way too large. So we just wouldn't be able to do a reaction. You could wait your entire lifetime and not get any significant amount of hydrogenation. All right. An alternative, and this is the alternative we're going to recommend here, is that you add certain transition metal catalyst. The one that we're going to use the most is palladium, but platinum and nickel are options in certain cases. And usually you'll take the palladium and absorb it onto the surface of activated carbon. And so that's why we get the palladium carbon. You won't see palladium just by itself. The carbon makes it so that the reaction happens in a reasonable amount of time. If you just throw a chunk of palladium in there, the reaction is going to be so slow that you might as well just not be doing it. So, all right, and you'll see here we add hydrogen across the carbon-carbon double bond, and we end up getting an alkane from an alkene. We can look at the heats of hydrogenation, or the delta H of hydrogenation, as a way of determining how stable a particular alkene is. So the way that you can do that is if you have two alkenes that when you hydrogenate them, they give the same product, then you can predict then the heat of hydrogenation will tell you which one is more stable. The more stable alkene has a smaller negative heat of hydrogenation. Let me explain by showing you an example. So here we have cis-2-butene and trans-2-butene, which we saw previously in chapter 10 of our textbook. So cis-2-butene and trans-2-butene. We know that the trans alkenes are more stable because there is less steric hindrance between the alkyl groups in the trans than there is in the cis. In the cis, there's a little bit of bumping that's going on, and it causes it to be a little higher in energy than the trans. Well, when you hydrogenate each of these, they both give butane as the product. All right, so they have the same product, but they have different starting points. You'll notice that the cis-butene gives us a negative 120 kilojoules of heat released in that process, whereas with the trans-butene, 115 kilojoules of heat is released. Because the negative 115 is a smaller negative number than the negative 120, that means that this was more stable to begin with. Now, to illustrate this a little bit more, I'm going to show you an energy diagram that says the same thing. So here is an energy diagram. And again, so here we've got the cis alkene and the trans alkene. They both give butane. And so you'll notice down here that the butane, these are both at the same energy level, the product. However, the cis isomer is higher in energy, and therefore it gives off more energy when it is hydrogenated. The trans alkene is lower in energy, and it gives off less energy when it is hydrogenated. So we can tell what the difference in stability is. If we take the difference between the negative 120 and the negative 115, that tells us there's a difference in energy between the cis and the trans isomers of 5 kilojoules per mole. The trans isomer is 5 kilojoules per mole more stable than the cis isomer. So again, that trans isomer is 5 kilojoules per mole more stable than the cis isomer. Pretty cool. All right. Now, as far as the mechanism of hydrogenation, this is not a traditional mechanism with curved arrow formalism that we have been using previously. This mechanism is more of a cartoon. So I don't expect you to memorize how to draw this out or anything. What I do want you to understand is that it's a stepwise process, and it actually helps us to understand some of what's going on when we do hydrogenation. So we've got our surface of the catalyst, which is the palladium, and that surface will absorb hydrogen into it. And so when it absorbs the hydrogen onto that surface, we can also absorb an alkene onto the surface. The pi bond will coordinate with one of the palladium atoms, and then these things are free to move around, and the hydrogens will dissociate to form hydrogen atoms that are bonded to the palladium. Well, one of the hydrogen atoms will make a new bond. It will break the bond between hydrogen and palladium, break the bond between the carbon and palladium, and give us a new bond between carbon and hydrogen. And then the other hydrogen will come along and will make a new bond between carbon and hydrogen. What's kind of cool about this is that there's not just one of these at a time. You can actually get millions, billions of these hydrogen molecules and alkenes that are at the surface of a small particle. And in doing that, you can get lots and lots of reactions to occur. And in fact, for every palladium atom that there is, you can get many, many of these hydrogenations. So that's why it is catalytic, because the palladium is not consumed in the course of the reaction. All right, so there are a couple of things that are kind of useful that come from this mechanism. And one of those things is that the rate of hydrogenation depends on how many alkyl groups are present. So there's two really important things that the mechanism will tell us. One is that we get rapid sequential addition of hydrogen, and they occur from the same side of the alkene. So that alkene doesn't have time to like turn around so you can get anti-addition. You're always going to get syn addition. And I'll show you what that means in terms of reduction a little bit later, but we'll always get syn addition when we're doing hydrogenation like this. The other thing is that the more alkyl groups you have, the more difficult it is for the alkene to coordinate with the palladium. So we will find that this tetrasubstituted alkene is going to react much more slowly than a monosubstituted alkene. And if we just had ethylene with no substitutions at all, we would find that one would be very fast. All right, so let's look at number 36 on the in-class assignment. I'll go over to our document camera here. All right, so we have alkanes A, B, and C. We want to rank A, B, and C in order of increasing heat of hydrogenation. So the more stable is going to have the smaller heat of hydrogenation. So our for part A, our delta H of, and I'm just going to put for hydrogenation. All right, that delta H of hydrogenation for the one that's going to be the most stable is B. So B will have the smallest negative delta H of hydrogenation. The next one is going to be the slightly more substituted. So this one, the tri-substituted alkene, so C, and then the largest negative heat of hydrogenation is going to be A. All right, so most heat will be given off for A, and the least heat will be given off for B, with C in the middle. For part B, the question is rank A, B, and C in order of increasing rate of reaction with this. So which one's going to be slowest and which one's going to be fastest? So we'll put rate here? Well, this is not particularly interesting because it's going to be the same order. The one that's most substituted is going to be the slowest, so B will be the slowest, C will be faster, and A will be the fastest. But I could ask you either of those questions, and I want you to be able to answer either of those questions. Okay. So let's look at hydrogenation of other double bonds. All right, so doing hydrogenation of other double bonds. Carbon-oxygen double bonds, particularly those that are in aldehydes and ketones, can be fairly easily hydrogenated with hydrogen and palladium on carbon. And we'll see this in more detail in a later chapter, but we'll see that aldehydes can be reduced to form primary alcohols, and ketones can be reduced to form secondary alcohols. I will note, and this is an important detail, hydrogenation will not affect carboxylic acids and its derivatives. And its derivatives include things like acid halides, esters, acid anhydrides, and amides. So this is just something for the aldehydes and ketones. So here we've got an aldehyde, and when you reduce it with hydrogenation and palladium on carbon, you will get a primary alcohol, and when you do the same thing to a ketone, you will get a secondary alcohol. We will see this particular reaction again in chapter 20, in case you're curious, when we talk about carbonyl-containing compounds. Let's look at the hydrogenation of vegetable oils. And I bring this one up because it is a pertinent topic. It's important for understanding how a lot of vegetable oils will work. All right, so it's possible to take an unsaturated vegetable oil, and here I've got a picture of an unsaturated vegetable oil. This one is a polyunsaturated vegetable oil. And you can either partially hydrogenate it or completely hydrogenate it, depending on how much hydrogen you add. And so one thing about these vegetable oils, the double bonds that are in vegetable oils, the fatty acids that are attached to the glycerol, those double bonds are in the cis configuration. Because they're in the cis configuration, we'll find that the crystals, these don't form crystals very easily, and so these tend to be liquids at room temperature. Well, when you hydrogenate some of them, you will find that they are more easily can turn into a solid, and so they're more likely to be a solid at room temperature, and they're more likely to act like butter. And so we get, that's a partial hydrogenation. That's a partially hydrogenated vegetable oil. Just for the record, if you're looking at vegetable oils, which ones are healthier for you? The polyunsaturated vegetable oils are healthier for you. The downside of these polyunsaturated vegetable oils, like olive oil, is that they are more likely to turn and go bad. So they're more likely to get oxidized as time goes on because they have more of these allylic hydrogens on them. And as a consequence, they can turn rancid a little easier. Now, I use olive oil all the time. I have never had a container of olive oil go bad because we always use the olive oil fast enough that it doesn't have a chance to go bad. But in terms of storage for oils, these polyunsaturated oils are more problematic for long-term storage. All right, it is possible for the steps in the hydrogenation to be reversible. And when you have one of those hydrogenation steps that is reversible, all right, you'll find that you can hydrogenate and then dehydrogenate. And when that dehydrogenation occurs, it's possible that what was a cis alkene can be converted into a trans alkene. Well, by converting it into a trans alkene, you will find that it'll have a higher melting point, kind of like a saturated fatty acid, and so it'll act a lot more like a saturated fatty acid, and will in a lot of ways can increase your risk of high cholesterol. So trans fats are actually not very healthy for you. They're as bad, maybe even worse than some of these saturated fatty acids. So just keep that in mind. It's probably best in most cases to stay away from the partially hydrogenated oils. Go with the less processed polyunsaturated oils. Olive oil and canola oil are healthier than some of the solid oils that you would find. Whatever you do, don't go get a bunch of Crisco and use that all the time. That's a sometimes oil. Okay. We next want to look at alkynes, the reduction of alkynes. And the reduction of alkynes happens a lot like the reduction of alkenes, in that you can add hydrogen across the carbon-carbon triple bond. And we'll find that there's three different things you can do. One is that you can add two equivalents of hydrogen and it will get reduced all the way to an alkane. Two, you can add enough of the hydrogen so that you just get the alkene and you'll get what we call a Cis Alkene. Or you can do another type of reaction where you get anti-addition of hydrogen across a carbon-carbon double bond and you'll get the trans alkene. And as far as which one are you going to get, it depends on which reagent you use. And so we will look at which reagent. You could imagine there's scenarios where we want to do each of these things. And so that's what I'm going to show you now. So if you want to hydrogenate all the way to an alkane, so you want to completely hydrogenate that alkyne, then just use hydrogen with palladium on carbon like we did a little bit earlier. If you try to add just enough so that you'll do one of them, it's not going to work very well. You'll hydrogenate, and then while it's there, it'll hydrogenate this again, and you'll just get the alkane. You'll get a big mess of stuff. Mostly, it'll be the starting material and alkane, and not much of the alkene will be produced. So it's better just to, if you're going to use the palladium on carbon, plan on going all the way to the alkane. Here we have 2-butene, and we hydrogenate it twice, and we will end up getting butane. If we want to stop at the alkene, we need to use a less reactive catalyst. So if you want to stop and get that Cis Alkene, you need to use a less reactive catalyst. Now, palladium works really well, but when you have palladium absorbed onto carbon, it's just too reactive to allow hydrogenation to stop after just one equivalent of hydrogen adds. So to do that, we need to deactivate the palladium to some extent. We can do that by absorbing the palladium onto the surface of calcium carbonate. Calcium carbonate's a solid. And then that calcium carbonate is going to have some lead 2 acetate and some quinoline. And this is what quinoline looks like. And then the lead 2 acetate is just the PbOCOCH3 2. So there's 2 of those acetates that go with the palladium. And it turns out that this particular concoction of materials will deactivate the palladium just enough so that you only get one addition. So when it's deactivated, we say that it is poisoned. All right. So what I want you to remember is that the Lindlar catalyst has these components in it. And when I put hydrogen with Lindlar catalyst, then we're only going to get one hydrogenation. And that one hydrogenation will stop at the alkene. It turns out alkenes just don't react with the Lindlar catalyst. Only the alkynes do, which that's kind of a cool trick. So the Cis Alkene is just too unreactive to get further reduction. So here is an example of what would happen with our Lindlar catalyst. We add the hydrogen to our alkyne, and we stop after one addition, and you'll notice that we get the Cis Alkene, which is the less stable isomer. Here with 2-butene, hydrogen with Lindlar catalyst, and we get cis-2-butene. All right. And then for our final hydrogenation technique, we're going to look at the dissolving metal reactions of alkynes. And with our dissolving metal reactions, our dissolving metal reduction, we use an alkali metal like sodium, and then our source of hydrogen is our solvent, which is liquid ammonia. And then we add the elements of hydrogen, but not in the same order that we would in a hydrogenation. We add the electrons first and then throw the hydrogens in there. But the hydrogens end up added in an anti-fashion, so we'll end up getting the trans alkene. So here we go. Here we've got our alkyne, our just regular alkyne. Here's our dissolving metal reduction reagent, sodium plus ammonia. And again, that ammonia is the solvent. And then we get our trans alkene. And here is an example, the 2-butyne, and we'll end up getting trans 2-butene. Why? Well, I'm going to show you the mechanism, and this is not a mechanism that I will expect you to reproduce on an exam, but I want you to understand why it is that we get the trans alkene. And that's why I'm showing you the mechanism. And this mechanism helps us to understand why it is we get that trans. So first thing, our alkene gains an electron directly from the sodium. Sodium is really good at giving up electrons, so it gives its electron to the alkyne, and we end up getting what's called a radical anion. Now, that's a very unusual reactive species, very, very reactive. It will deprotonate the ammonia molecule, and so now we will have this radical. Well, that radical is now electron deficient, and it will take another electron from a sodium, and that will form a carbanion, which is a vinyl carbanion. That vinyl carbanion is, it will arrange itself so that the R groups are trans to each other, and then we'll deprotonate the ammonia, and we'll end up getting this trans alkene. Pretty cool. All right, so let's look at the summary of the dissolving metal reaction. So when we have the dissolving metal reaction, we get this this vinyl carbanion intermediate that arranges the two alkyl groups so that they're further apart. If we try to put them closer together, this is higher in energy and not very favorable. It'll just cause that R group to flip back over to the other side. So these are interchangeable, but this one is lower energy. And as a consequence, we'll end up getting the trans alkene. Pretty cool, pretty cool. So now let's put all these reductions together, and then we'll do a problem on the in-class assignment. So here is our summary of alkyne reductions. If we reduce an alkyne with just regular palladium on carbon with hydrogen, we will reduce it all the way to the alkane. If we use hydrogen with the Lindlar catalyst, which again has the lead to, well, it's got the calcium carbonate, lead to acetate, and the quinoline, then we will get a cis alkene. And if we use the dissolving metal reaction, we'll get the trans alkene. This selectivity is very, very useful. So it's very, very useful. So now we're going to go over to number 42 on the in-class assignment, and we are going to come up with our products for this. All right, so here, give the products of each reaction, assume the reagents are present in excess, meaning that we have plenty of hydrogen and that the catalyst is ready to go. Well, we know that hydrogen with palladium on carbon will reduce both alkenes and alkynes, so we really just need to figure out how many carbons are here. So I'm going to number it here. 1, 2, 3, 4, 5, 6, 7, 8. So we've got 8 carbons there. That means we're going to get octane. 1, 2, 3, 4, 5, 6, 7, 8. So there is our octane that we're going to get. Again, we're going to reduce both the alkene and the alkyne all the way to the alkane. With the Lindlar catalyst, remember with that, we are going to get, reduction of our alkyne, but it will not affect our alkene, and we will get syn addition. So what that means, 1, 2, All right, so we're going to reduce this one to a cis alkene, and this one will remain a trans alkene. So 1, 2, 3, 4, 5, 6, 7, 8. That will work. All right, and then finally on this one, we are going to get we'll get reduction of the alkyne. It will leave the alkene alone, and we'll reduce the alkyne, but it will reduce it to a trans alkene. So 1, 2, 3, 4, 5, 6, 7, 8. All right, so there is our carbon 5, carbon 6 bond, and then between 2 and 3, we'll also get a double bond. All right, so there we go. That will give us that trans alkene. All right, we've got one final topic in reductions that I want to look at before we stop this particular video, and then we'll go to oxidations. So we want to look at the reduction of polar bonds where carbon is bonded to X, where X is something more electronegative. It could be oxygen, it could be a halogen, it could be any number of things. In this case, we're going to be using lithium aluminum hydride, which we will see is a useful reducing agent that we'll use at later points as well. So here is lithium aluminum hydride, and if we add an alkyl halide with lithium aluminum hydride, we can change the halogen to a hydrogen. And this is a useful reaction that we might want to do at some point. We do have to do a second step where we add water. I'll show you why that's the case here in a minute. But it is to protonate so that we don't have the lithium aluminum hydride is pretty reactive. All right, we can also open up epoxide rings using lithium aluminum hydride, and that will form an alcohol. All right, and so here when we hydrogenate, or when we add the lithium aluminum hydride, hydrogen will come in and do an SN2 reaction on one of these carbons and open it up. In this case, it did it on the left carbon. If you've got one that you've got one of the carbons is less substituted than the other, it will go to the less substituted carbon because it is an SN2 reaction. So you can open that up and you will get an alcohol. All right. The mechanism is not too terribly difficult, and the reason that I'm showing you this mechanism is so that you understand why we are getting you understand why we have to add the water in a second step. So it does follow an SN2 mechanism. All right, so we add the hydrogen. The hydrogen comes along and it will act as a nucleophile, and the halogen will be lost. And so here we form that alkane. We've lost the halogen, and it turns out that this chemical is reactive, and so we add the water to neutralize that. So for unhindered alkyl halides, it goes really, really fast. For secondary and tertiary halides, it will work, but it's not nearly as fast. And with lithium aluminum hydride, we don't have a competition with elimination reaction, so that's a fortunate thing. All right, so again, SN2, so it will go to the less substituted carbon. All right, and that is in the case of the epoxides. So let's look at number 14, and this will be the last thing in this particular video. All right, so lithium aluminum hydride, we do the reduction here, and we're just going to convert that into an alkane. So we'll just do 1, 2, 3, 4, 5. All right, so we'll get that. And we're not going to worry about the rest of the stuff, but you will get a lithium chloride and some aluminum containing compounds. All right. And then on this one, the lithium aluminum hydride will come in and react with the less substituted carbon. So it's going to come into this bottom one, and this will be stereospecific. All right, so we will get OH. The water is to protonate the alkoxide. All right, so that CH3 is still there. I'm going to put CH3 so everybody's clear what that is. And then our hydrogen will be here. We don't need to indicate the hydrogen, but we do have 2 hydrogens on that atom. All right, so we do have 2 hydrogens on that atom. And we end up getting that. So here we go from something that has 2 stereogenic centers to something that has 0 stereogenic centers, which is kind of interesting. We will not get hydrogenation at this other carbon because it will always go to the less substituted carbon. All right, so that is the end of the reduction section. And so we are going to stop the video here, and we will do the oxidations in our second video.